about the relationship between machine and human decision making. And this is a discussion with Professor Daniel Kahneman. So it doesn't need much introduction, I think, but anyway, I'll do a little bit. So Danny is a psychologist and an economist. Is very well known for his work on psychology of human judgment and decision making. And he was awarded the 2002 Nobel Prize in Economic Science. And it mainly defined the cognitive basis for human errors based on our heuristics and bias. And his 2011 book, Thinking Fast and Slow, that you see here, summarizes his theory and a lot of experiments to support this theory. He's very interested in AI and machine decision making as well, not just human decision making. So much that in one of our discussion, he told me that if he were a young student again, he would go and study AI rather than psychology, which you know, but we're very happy to hear. But I think that with this work, even if it's not core AI, is really an amazing and great inspiration, as you may have seen also from the talks of the Turing Award winners that we heard yesterday. An inspiration to build and advance, to build machines that can be human-level AI and also to advance, you know, the technology. So the structure of this informal discussion is that it will be all about having his, you know, opinions and his thoughts about AI and machine decision making, but you know, Jeff and Joshua and possibly Ian, if he comes, we will, you know, try to get as much information as possible from Danny to advance AI. So I will start by just asking Danny, you know, to briefly summarize in his own words the main, you know, ingredients of his theory.
Okay. Well, the first thing I should say that the terms System 1 and System 2 are not mine. They just happen to be the first 100 pages of the book, which for most people are the only pages they read. So it's...
out of...
I wanted to make just a very few comments about the way the terms were used last night, you know, which was the first time that I heard them used in the context of AI. And there was one remark, I think, that Joshua made, that System 1 is pre-linguistic. That surprised me because, so far as I'm concerned, System 1 certainly knows language, understands language, has what System 1 has, so far as I'm concerned, the most interesting characteristic, is that it has a representation of the world, and the representation of the world doesn't generate expectations, specific predictions for what's going to happen next. You really have no idea what I'm going to say next. But what is happening is that when I say something, usually you're not going to be surprised. That is, it's this reconciliation of what happens with a model, with an existing model, and an existing representation, which is something fairly miraculous that System 1 does all the time, almost continuously. So it determines when we're surprised and when we're not surprised. When we're surprised, System 2 typically would kick in. That is, and now the difference between the two was something else that I noted yesterday. For me, the main difference would be implicit versus explicit. And so implicit, it's obvious what it is, but explicit, that sound to me, you know, very naively in terms of the distinctions that you've been making, as if it does involve something like the manipulation of symbols. In terms of introspection, this is certainly the case. And what System 2 is specifically capable of doing, that System 1, I think, doesn't do, is serial sequential operations. That is, where you have to move through steps. You could move fairly fast, but there are distinct steps that you've got to move through in logic, in reasoning, in mathematical computations of some kind. So those would be the differences as a psychologist, and it wasn't exactly the way the terms are being used here. As a psychologist, well, there's another psychologist who talks a lot about AI and knows about it much more than I do, that Gary Marcus, who is not terribly popular, I think. But I'm influenced by him, and I think that there is actually, what I note is that over the last couple of years, there has been a kind of rapprochement between psychology and AI. I mean, the recent debate between Joshua and Gary Marcus clearly indicated that. And Gary proposes something that seems very natural in terms of what I have said, which is a sort of hybrid architecture, which I know is not popular here. This is not what people are trying to do, but if you're looking introspectively at the way the mind works, in the same way that by introspection you'd say some thinking is automatic and some is not, System 1 versus System 2, you would get to that distinction between implicit and explicit, where explicit sort of looks like symbols.
Thank you. So, Joshua, maybe you were more, how would you agree with his definition of implicit versus explicit rather than conscious versus?
Yeah, it's just different words for essentially the same thing. Regarding the language thing, so yesterday I probably didn't have time to express my thoughts as much as I would have liked. So I totally agree that System 1 has very powerful, is an important part of linguistic abilities. But it's let's say, you need both of them, I think, to get the kind of linguistic abilities that humans have. And I think it was Jeff talking yesterday about some of the mistakes that current state-of-the-art transformers do in natural language processing, which give the impression that the current systems understand the world in a very incomplete way. And of course, one aspect is that they're not grounded in perception, but there may be also something else about what linguists call systematicity or systematic generalization, which I tend to associate with System 2. So when we use language in a way that we reason with it, and we are able to use it in completely novel situations, I have the impression that it belongs more to the System 2 part.
Like everybody else, I'm terribly impressed by things like Google Translate and so on.
But you should look at the mistakes, because this is your specialty.
There's been huge progress in that, no question. There is, and I've been looking at some of the outputs of Transformer, and what strikes me about these systems is they don't know what they're talking about. And this is really a significant requirement, I mean, so far as I'm concerned. So the fact that they sound like language, this is something that somebody could say, but what are they saying? That is, what do they know about the world? And it seems to me that all the progress on language processing is at the surface of things.
Shallow.
Yeah. There's no depth, there is no content, it doesn't know what it's talking about. And what it would require for a system to know what it's talking about. And that I think, is a profoundly important question. It would clearly have common sense. It would know something about the world. And I mean, I think it's an interesting question for everybody to ask themselves. What would it take for someone? It's a new version of the Turing test. What would it take for a computer to convince you that it knows what it's talking about?
Mm-hmm. Yeah.
But clearly it would need a model of the world. So right now we're learning these language models using only text. And there's a lot of knowledge about the world which we get by being in the world and interacting and perceiving. And then, in a sense, language is just the, the labels on top of these
so
things.
that's what we were saying, yes.
Can I say something about that?
Yes, of course.
I think it used to be the case that if you'd said, we can tell whether it knows what it's talking about by whether it can say the same thing in a different language, people would have said, yeah, that'll show it knows what it's talking about. So we do that, and then people say, oh, that doesn't show it knows what it's talking about. So then we say, well, maybe it would show it knows what it's talking about if you can show it a picture and it can describe what's in the picture. But that doesn't seem to count anymore either. So there is a slight worry that whenever you come up with something, someone will say, well, but it doesn't really know what it's talking about. It's just doing behavioral things, It satisfies your test, but it doesn't experience it.
Well, a good example of this, perhaps in sort of recent events, is the fact that until before the transformer revolution, the best performance of computer systems on Winograd schemas was about 60%, where chance is at 50%, and now it's 90%. That doesn't mean any of those systems have any level of common sense, but there is enough data in the language to lift the type of ambiguity that people in sort of in AI kind of thought required common sense. They don't. Now, that said, a lot of people are working on sort of grounded language learning, right? So there's a lot of efforts, Facebook, Google, and other places to create virtual environments where you can have agents operate and then perhaps use language to kind of describe what they're doing or listen to what we're doing. There's such a project at Facebook called Habitat. And that's the hope of sort of grounding language into some sort of reality. It's a virtual reality, but it's a kind of reality. Mm-hmm. The reason for doing this is that the bandwidth of information you get from visual input or other types of perceptual modality is much, much higher than what you get with language. So that's, how do you learn only through language all the intuitive physics that if I put this pen on the table and I let it go, it's going to fall, right? But like how much text do I have to type to kind of describe the situation? Whereas I could have a sort of, physics simulation engine in my head that I learned by observation. That's I think, the crux of common sense.
Yeah, I mean, one of the things I was wondering about in asking myself that question, how would I know if it knows what it's talking about? It's hard to imagine a device without a sensorium, without some way of connecting to the world of reality. Mm-hmm. So that if it's only words, it's going to be difficult, and I agree with Jim, to distinguish. But even if it is words, what you would really want, and that's common sense and causality, you would want the inferences that people normally can make about the world, and they can make about the world because they know the world. Yeah. You would want those inferences to be made, and you would, and I don't know what tests we would have to conduct to sort of construct. Does it answer that way because it knows the world, or just because it has a rote answer? Mm-hmm. And it's very much like rote learning versus learning with understanding. We know that there is a difference.
Yeah. So I want to come back on the word understanding because it might be a bit misleading, and I want to channel Tom Dietrich here, who wrote a nice piece about this. Understanding is not black and white.
I agree.
And so the current models do understand a lot of things about our world, and we're building models that have better common sense because they will have a model of the world. Children understand some things and don't understand other things, so we know it's gray levels. And so when people say, "Oh, your machine learning system doesn't understand," what they really mean is they don't understand this particular piece of knowledge about the world. And so we're making progress, and it's going to be gradual.
So let me introduce another aspect that I noticed, that I mean, as far as I understand, in your theory, you say that you show that in our decision making, some tasks we start addressing them and solving them with our system 2 capabilities, and then after a while we are familiar enough with them that we pass them to the system 1. And this dynamic aspect, I mean, I didn't notice it in the AI, you know, approaches inspired by your theory. What do you think about that?
I mean, it may not be necessary. I mean, you know, we learn driving that way. So we learn driving in a way that is explicit. So everything is explicit in driving. Mm-hmm. And then with experience, the explicit becomes implicit. Yeah. And that frees resources so that you can drive and talk at the same time, yeah, which at first you cannot do. Whether that is an essential aspect of cognition that should be reproduced in human-level AI, or whether it's simply that it takes people time to learn something that a machine would learn much faster, I don't know. I'm not sure that skill acquisition of that type, mm-hmm, with the move from explicit to implicit is really essential.
So my guess is there is a fundamental reason for this, and in my words, it would be that it's much easier to create new combinations of words, but also concepts in the system 2 realm. And then once we've put this in place, we can compile it to something automatic in system 1. But for system 1 to have jumped into this new behavior without the system 2 part might have taken a lot more practice than if you didn't have system 2. That's what I think.
Mm-hmm.
So yeah. I think there is the reason perhaps that we need to sort of pay attention to what we're doing when we learn to drive and we can't do anything else is because we have only one system 2 engine. Yeah. And so we have to devote it to whatever task is at hand. But then once this skill is compiled into system 1, then then becomes part of the subconscious, and we can automate it. In fact, the system I described at the end of my talk yesterday is pretty much of that type. So you have a world simulator that simulates what the cars around you can do, and from that you can predict a number of different scenarios. You can plan an optimal path using kind of a system 2-like approach where you find this optimal path by optimization. But then what the system does is that it uses that to train a reactive policy, a neural net that just predicts what you have to do. That's more like a system 1. So yeah, I mean, I think it's definitely possible to do this kind of thing. And system 2 is expensive, so you can only afford one.
So can I make a comment about system 1 and system 2?
Yeah.
I have a very different picture, which is that if you have a big parallel neural net, or a big neural net with lots of neurons, there's certain things that you can do in one operation in the neural net. It's like a huge instruction set machine. In a few hundred milliseconds, the neural net can do a forward pass, maybe do some up and down, but it can settle on something. And that's a sort of primitive operation that's incredibly powerful. You can see an analogy in one operation. But ultimately, in the end, you can get to tasks that are so difficult, even this great big neural net can't do them in one operation like that. And so now it has to go sequential. It has to break the task up into several operations, and typically what that involves is remapping bits of the task onto the neural hardware. So the same neural hardware gets used for different bits. Like if you think about the hierarchy that we know about, there's the universe, and then there's clusters of galaxies, and then there's galaxies, and it goes all the way down to protons and then electrons and quarks and things. And we can't think about that all at once. What we have to do is we use the same hardware for thinking about structures at all these levels, but we just map reality onto the hardware in different ways so that we can cope with immense hierarchies like that with limited hardware. And I think what's happening is that as soon as you get a complicated task, you have to map the task in several different ways and reuse the same hardware. And so really what's going on is that we've got these very powerful operations. You can see things intuitively in one step. But when things get more complicated, you have to use that several times. And then there's a problem of how do you decide how to use it several times. But that's the kind of problem system 1 can solve. So seeing a plan, for example, seeing a plan for how to do something is a primitive operation. If it's a complicated plan, you might need to break it up into several primitive operations. And so it seems to me that System 1 and System 2 is quite closely related to what you can do in parallel and what you have to do sequentially. And my view about symbols is that there's symbols on the input and there's symbols on the output, and that's the only place there's symbols. In between, there's these massive vectors causally interacting with each other. And the idea that there have to be symbols in between is like the idea of, an idea that I'll attribute to Koslin, although it's a bit unfair, which is that we know what pixels are. We know how to make a picture out of pixels. And what's inside must be like pixels. If all you've got as a model of how to make images is pixels, you think there must be pixels inside. And I think the people like Fodor and Polishin were making exactly the same mistake with symbols. They knew what symbols were. They could see operations on symbols when you do them on paper. They thought that's what must be inside. But what's inside is totally different. It's always these huge operations with massive vectors. Now, Danny actually had a very good counter-argument, which is the limited bottleneck, and I don't know what to do about that.
Well, I mean, you know, what you described is completely compatible, I think, with my view of System 2. The question is, what would happen at those junctures when you're passing something, when you're turning something from parallel to serial? Parallel serial is part of the definition of System 1 and System 2. System 1 is massively parallel, and System 2 has to operate. So the descriptions are not all that far apart. Subjectively, I would think it does feel that when you're operating in steps, although you may be highly skilled and you're not consciously reverting to the program necessarily, what you are operating on feel like symbols. They're representation of what you did in the previous computation.
Yeah, one of the things that, to kind of rebound on what Jeff just said, there's a lot of things that may look on the surface like symbol manipulation, but internally may not. And so it's kind of one of the points I was making yesterday as well, that, you know, is it possible to replace symbols by vectors or patterns of activities, and logic by continuous functions, hopefully differentiable functions, so we can make it compatible with gradient-based learning, with deep learning. So I think that's really the big question. And in the end, it may not look at all like you know, the sort of orthodoxy of symbol manipulation, which is what some of the symbolists will really dislike this, because they insist that it has to be symbol manipulation, and you know, if it looks like symbol manipulation but is done with vectors, I'm not sure they'll be happy.
I accept that.
So maybe let me speak against my friends here. One of my students who's been very successful, Dima Badanao, has proposed this idea that discretization in the middle of the System 2 sequence might be useful because it would facilitate the communication between the different parts that have to exchange information by reducing the number of choices, essentially, that you know, things that can be communicated, so as to make those pieces of computations, those modules, more plug and play, more interchangeable, right? So it's going to be harder for one module to have some co-adaptation with a module downstream if it has to go through a bottleneck that's more discrete in nature than if it can send very rich vectors. That's an argument, at least. That's interesting.
Yeah, so another thing is that, you know, a lot of symbolic reasoning, logical-based reasoning deals with symbol, the input and the output, and also in between, because we want also like 100% correctness about some task, right? About solving some task. Is that?
But do you think that symbols can give you that? I mean, many problems are much too complex to be reduced completely to symbols.
No, I'm saying that for some problems where you can describe them exactly with symbols and symbolic manipulations, then I think that some people would think that it would be, I would say, why would you want to do it in a different way, which maybe requires much more resources and computing time and examples. If you need more flexibility, yes. But if you don't, because the problem is very well defined and it has to answer correctly, then I think that that's why some part of this community has decided to look at this problem very well defined with the symbolic manipulation, all the steps, not just in the input and the output, right? So would you say that that's also something that can be approached instead with an internal non-symbolic?
My view
so
is
system one.
My view is that kind of formal reasoning with symbols is one of the very last things we learn to do. I think you get to be a teenager before you can do formal reasoning with symbols, or maybe you have to stop being a teenager. But the advantage of having a big vector is you're simultaneously checking millions of soft constraints, and that's a lot of what common sense is. So there's this old experiment that by Phil Johnson-led, or Wason or somebody, where you have to do a little bit of reasoning, and I make it abstract and you can't do it, or you make mistakes, and I make it concrete, and it's no problem at all. And the essence of a symbol is that it's got no content, it's only got identity or non-identity with another symbol. And the essence of a vector is got a huge amount of content. It's got all of these things going on at once. And I think that's a large fraction of what common sense is.
So let me touch the last, because we have just 2 minutes, so let me touch upon one last thing. So our system one, if I understand well, can deal well with causality. Can have few pieces of information and build the whole story, right, because of causality. So now, machine learning and deep learning do not deal well with causality yet, at least. No? So then that's a difference in this analogy where system one is more like machine learning approach, system two, the symbolic.
I mean, that's clearly something that babies are born with, and it becomes explicit in the first few months. They're born with two kinds of causality, with physical causality and with intentional causality. So both of these are built in and are recognized very early, and that's, it would seem, is really a fundamental part of human intelligence. So you would expect before artificial human level intelligence, you certainly would expect that problem to be cracked. And it's interesting that it seems to be a primitive. It seems to be a given. You start from that in the development of intelligence.
I think there's two issues with causality, right? One is using causal inference. So you have a model of the world, and you're trying to figure out, like, how can I affect the world to obtain a particular result? And this is what Julia Pearl and others have worked on. And then there is the problem of establishing causal relationships from data or from intervention, but sometimes without intervention. It turns out it's possible in certain cases, and that's where deep learning can help. I mean, you need a learning engine of some kind to establish causal relationships. So there's a lot of really interesting work in this area. Certainly one of the first people in the machine learning context to work on this was Bernard Cholkopf, and some of his students, David Lopez-Paz, Léon Boutou at Facebook, and a bunch of other people. So Léon Boutou in particular, where Martin Najowski and others have come up with this idea of causality based on invariance, which is really interesting. But humans are not particularly good at establishing causality from observation or even from intervention. If we were so good at it, I mean, we attribute causes to things that don't really have any cause, right? We Well, animism, for example, is giving causes to natural events. In fact, probably all of religion is pretty much that way. So if we were really good at causal inference, we wouldn't have any religion. I'm impersonating Jeff right now. We're not so good at it. I mean, so the question is, do we need an explicit mechanism for discovering causality, or is it just a natural consequence of having an engine that establishes, predictive model of the world? If you have a predictive model of the world that can predict the consequences of your actions, then you have a causal inference engine.
So I just want to add that actually yesterday I quickly mentioned some work that we were doing in my group, that some of it is going to be published at the next iClear, where we use meta-learning and neural nets to do causal discovery. In other words, to find what are the causes and which causes what. And so I think this is just the beginning where we can use gradient-based methods, which belong more to system one, in order to discover causal structure using neural nets.
So I think I have one question that can clarify.
Very short, because we have
how
to
we
finish.
differ. So when you're using system two sequentially, is each individual step of system two a call to system one?
Oh, I would think so.
Okay.
Yeah, it's not completely separate. Clearly, the meaning is in system one. But it's a sort of shortcut that you're manipulating. And that sounded very compatible between that description and what you were describing.
Okay, so I think that, you've seen, we could continue for hours here to exchange ideas and to get more inspiration about how to build, advanced AI systems. But we have to stop here. We have an invited talk. But I really would like to thank the Turing Award winners for coming back this morning to discuss with Danny, and for Danny to be here with us. Thank you very much.